Okay, so today we're going to finish talking about the main part of the processor. So it's also we're going to wrap up the main part of parallelism. So I guess given that we don't have class on Friday, as you know, and given that we have Thanksgiving coming up, I guess you realize it's starting to get down towards the end of the semester, and I guess you have one project left. So quick in the news, just to show you that we weren't wasting your time in Project 2. This is one person's guess at what the next hot computer science job is going to be, and it's going to be Hadoop Guru, and that's you guys, right? So in particular, there's a couple nice quotes here. There's a nice quote from Mike Olson, who founded a company called Cloudera, which is one of the main Hadoop vendors right now. And Mike's a graduate of our department, and he's very involved in the department. You'll probably see him around. And the other thing here is that the good news is that Hadoop experts aren't born; they're trained, and in some sense, that's what we think we're doing here. So if you read this article, you'll see that you guys have a real leg up on a lot of other people that are not taking this version of 61C, where the first time they see Hadoop is when their boss dumps it on their desk and tells them to make it work. So that's in the news. So let's jump into the last topic. Again, we're looking within a single core. And we're trying to make things go faster with parallelism, and we're doing pipelining. A couple things I just wanted to mention, and this is straight out of the book. But we talked about when we first introduced pipelining the idea that you use registers in between the different stages of the data path to make it so you can run those stages all at the same time. And we never really talked that much about how the control changes when you do that. And so I just took a couple pictures out of the book, not because I want to explain them, but because I want you to go make sure you read this part of the book. And so this is one of the figures from Chapter 4, where it shows basically how those registers, right? This is a register that's after the instruction fetch and before the decode. This is the one that's sitting right before the execution. This is the one that's sitting before memory, and this is the one that's sitting before the write back, right? So you remember all those registers. And you can see that what happens is that the control gets passed along those registers along with all the other data that's coming out of each of those stages. And then, given that, right, so these registers are actually different sizes, okay, or they can be, and that's what this picture shows, all right? And then, I don't expect you to go through this right now, but what you can see is we have all the old control signals that we had before in the previous architecture, except now they're being driven by things coming out of the registers, right? Rather than necessarily by things that are coming out of the instruction memory, okay? So these two pictures, when you go look at them in the book, you'll see how we take that notion of control that we came up with when we had, the hardware and the software, the software and the hardware meeting, and this is how it actually gets implemented in terms of the wiring. Okay, I just wanted to remove a little of that mystery. Okay, but the book goes into gory detail on exactly which wires have to be coming out of where and going to where to make all this work. Okay, and then it gets more complicated. Remember we talked about structural hazards and other types of hazards and data hazards that we were going to solve through forwarding. You also have to get extra wires in here to do the forwarding. And again, there's another 10 iterations of this diagram that show you how those different types of forwarding get added in as well. Okay, and so a lot of times you're forwarding something from a register into one of the functional units. Okay, so I just wanted to get that out there so that it wasn't a complete mystery. And then where we were last time is we talked about sort of two types of hazards for pipelining. Structural hazards, meaning that two instructions needed the same resource at the same time. And the examples we had there were the memory, which is, remember, we fixed that by having two caches, a separate instruction cache and a separate data cache, right, at level 1. That solved that problem. And the other problem was the register file. And we had to be a little trickier there, but we took advantage of the fact that reading and writing the register file is relatively cheap. As long as it's less than half a clock cycle, then you can write it in the first half of the clock cycle and read it in the second half. And so we can get rid of structural hazards that way. Okay, so structural hazards are pretty easy. Then we spent a bunch of time talking about data hazards, having to do with one instruction needing the output of something that a previous instruction did, and making sure that that all works in terms of timing and clock ticks. Okay, and we talked about different ways of doing that. There's one more thing I want to show you on that. And then what I want to finish talking about today is a third type of hazard called a control hazard, which is when you're not necessarily taking the straight path through the code. How do you deal with the fact that you might have to jump to a different instruction while you're trying to pipeline? Okay. So those are the three types of hazards, and these are the things that make pipelining, a little more complicated than just simply putting registers in between the different stages. All right, so in terms of data hazards, I just wanted to mention one thing. So we want to implement these two things. We want to add B and E to A, and we want to add into A, and we want to take B and F and put those into C. And if we do it this way, then we've got a data hazard, right, between the load of register T2 and then the use of register T2 in the subsequent instruction. And remember, the way we solve that is by stalling. Okay, good. Thanks for catching that. All right. Okay, so now you guys had time to figure out what to do. What can you do here, right? In order to avoid that, in order to avoid that hazard, we can actually change the order of the code. Okay, so we can run it this way. So we can basically take, we can put an instruction in between the load and the use, right? Because remember, this is a load use hazard. We can put a different instruction in there, and then get reasonable work done. Get useful work done while we're waiting for that register to be written. Yeah. Yeah, so that's a really important point, right? If we're going to count on the compiler to do this, okay, that means we're going to need a smarter compiler. That means it's likely that compiler is going to take longer to run. So compiling your program might take longer. And the idea is that trade-off worth it? And the answer is, in general, yes, it is, because you compile once you got all your bugs out, you compile once and then you run it forever, right? So you amortize whatever extra cost. Now, compilers have different levels of optimization, and you can turn off levels of optimization to make the compiler run faster, while you're in debugging mode. And then once you have your program working, then you can turn on the optimization and make sure things still work and it'll go faster. But in general, yeah, it's this kind of typical trade-off between kind of upfront time that you pay once and then amortize it over multiple runs. In general, that's usually a good deal. It's usually useful to put the cost in that process you're only going to do once rather than pay the price every time you come through a piece of code that looks like this. Okay? But this is an example of where the compiler can help you. And actually, some hardware will do this automatically, too. We'll talk about that briefly. But there's hardware that's smart enough to recognize this problem and do a reordering, which is pretty interesting. We're not going to draw those circuits, but you can do it in hardware too. Okay, so make sure you understand this. But here we go from 13 cycles to 11 cycles. Why? Because there were 2 stalls here that we got rid of. And the program gets exactly the same answer, which, by the way, that's our rule. If you don't get the same answer, you can't do it. Okay, it's a little boring, but that's the rule. Okay, if you get a different answer, that's called a bug. Okay? All right, good. So so we talked about structural hazards. We talked about data hazards. Last thing we got to talk about is this idea of a control hazard. And we'll talk about it mostly in terms of branches. Okay? You also have issues with jumps, but let's talk about branches. And branches are particularly tricky because you don't know until you evaluate the branch whether you're taking it or not. Okay? And so, if you're pipelining ahead, sometimes, you're sort of working on the next instructions, but you don't actually know for sure what the next instructions are going to be. Okay, and that's a problem. So a simple thing you can do is just not pipeline when you hit a branch instruction, so you can stall. Okay, and if you stall, it kind of looks like this, right? So let's say we're doing a branch on equal. At what point do we know which branch we're taking? Which of these stages, 1, 2, or 3, 4, 5? When do we know when we're taking that branch or not? Yeah, after the ALU, right? After the execution step, right? Because that's where we check the equality. And remember, we use subtraction, to do that. If you subtract one from the other and the answer is 0, that means they were equal. So that's going to come out of the ALU. Now, what does that mean? That means, so that means, we don't know for sure until this instruction, what instruction to fetch from the instruction memory. Okay, because the result of the comparison has to come out of the ALU, and once we have that, then we can go look in instruction memory and get that instruction. So if we wanted to stall, we'd have to stall not just for a single instruction, but we'd have to stall for 2 instructions, which is a pretty high price to pay. So what else could we do besides stalling if we were willing to change the hardware? Was that a hand? Oh, was a hand back there, yeah. Yep, so we could be optimistic, and we could try to predict what's going to happen, and if we're right more than we're wrong, that'll be good, and then we just need a way to recover if we're wrong. So that's one thing we could do. What else could we do? You had your hand up. What did we do for load word? We forwarded? Oh, okay, so well, you can change, right. So we're going to change, there's another trick you can, okay, good. You can change the order of the code a little bit. So that's another thing we can do. And then anything else we can do? Oh, okay, you could start both threads at the same time and choose one, but we don't have enough hardware to do that. But you could certainly add more hardware. Oh, okay, you could try to start both paths, but then for sure you're going to have to kill one. And so then you're always killing one. Okay, so that is a hand, yeah? Yeah, we're going to, okay, so you can reorder and start the next instruction. Well, okay, and let me show you a different thing that you guys hadn't come up with, which is you can actually move the comparison, because I told you got to add hardware. So you could actually add hardware so that you can do the test earlier, okay? So remember, we were using our general purpose ALU, right, which is this big, powerful thing that we use to do all our integer arithmetic and all our logical operations. We were using that to check the branch condition. And most branch conditions are pretty simple. They're either equality or inequality, or maybe based on the sign, right? And so those are things that you could test with hardware that's cheaper than sort of a general purpose ALU. So what you could do is you can push the branch comparison up a stage and add some extra hardware so that you can do that branch comparison in stage 2. Okay, then once you've decoded the instruction, you can make a decision and then decide which way to go, right? You could do the comparison and then decide which way to go, subject to data hazards, of course. Yeah?
In that second phase, we already have first an
Yeah.
And finally, this branch submitted.
Right.
So wouldn't that actually make, it sounds like it would be the longest stage.
Okay, so there's a good question, which is, we're already doing a bunch in stage 2. Do we really want to do more? And the answer is going to be, remember what we're striving for is a balanced pipeline where all the stages are about the same length. And furthermore, our clock rate is going to be dictated by the slowest stage. So as long as 2 isn't already the slowest stage, and we can squeeze in a little more work, it's going to be a good deal. If for some reason 2 is the longest stage, then this is probably a bad deal because it's going to make your clock tick slower. Okay? But in general, 2 isn't the slowest stage. Yeah.
But then in this case, if you don't do anything else, won't you still be losing one, not a clock cycle, but one of those little ones?
Yeah. So, well, it is a clock cycle because we're doing every stage is a clock cycle now. But so what we've done here is we haven't fixed the stall. We've just gotten it down from 2 to 1. Okay? So that's an important point. So we haven't gotten rid of that stall completely. You're still going to skip 1 clock cycle, and we've got to fix that problem. But remember, before we did this, we had 2 clock cycles we had to worry about. Okay? So, we've cut the problem in half at least. Okay, now here's sort of a bonus question, which is if you don't want to implement a completely new ALU, right? Because remember, to do that subtraction was expensive, right? Because you're basically running the adder and you're doing all the carries, and that takes a lot. Can you think of a more efficient way in terms of time and gates to do an equality comparison? Somebody, yeah, in the back.
If you had an XOR,
Yep.
and you XOR 2 16-bit inputs, and then negated the output, it would be positive when they're both the same.
Yeah, so certainly if you use if you XOR the inputs, right, and then negate it, that'll tell you negated. It's good. I was going to say OR them together because you want 1 bit at the end. So what you'd do is you would do the XOR, you'd OR them together, and then you'd negate it.
One XOR with 2 16-bit inputs.
Yeah.
On the end, output 1, the 2 inputs is 0 and 1.
Oh, well, yeah, but you want 1 bit coming out, right? So.
One XOR only has 1 output.
Oh, right, but you'll have 16 of them, right? So bottom line is, I don't want to get into a long discussion of this, but bottom line is you're right in terms of the operation is you want to, another way we were using subtraction for equality, but you can also use XOR, right? Because XOR is going to give you 1s if they differ and 0s if they're the same. So if you get all 0s on all the bits, that means that they were the same, okay, bit by bit. Okay, so we can make something faster than the full-blown ALU that we were talking about before. That's the main point. Okay, and then we're going to put that in stage 2. So if we do that, as we said, we still have a stall, but now it's only one slot, not 2 slots. Okay, so that's one thing we can do, but we still have a problem. So what else can we do? You guys already figured this all out. One thing you can do is you can predict the branch, and then if you're right, you just keep going, because remember, right? And if you're wrong, then you've got to take whatever partial work you've done, get rid of that. That's called flushing the pipeline, and then fetch the right instructions. Okay, and if you look in the book, they talk about how to flush the pipeline. It's actually not that hard. It turns out that if you set the control bits to 0, right? Because the only thing that's going to impact instructions down the road is if you write a register or write memory. So as long as you shut off the control flags that would say write the register or write the memory, then you won't actually make any changes that anyone cares about. So you can set the control bits to 0 and then let those instructions finish and add the new, bring the new instructions in. Okay? So there is a cost for guessing wrong, but you can recover from it. It doesn't give you the wrong answer. That's the important thing. And so the simplest thing to do, of course, is to predict that we're not taking a branch. So for every branch, our prediction is going to be that we're not going to take the branch. Okay, and why is that? Right, because, well, there's 2 reasons. One is that that's our logic, right, is we always go to the next instruction. So if we don't take the branch, we fall through to the next instruction. Okay? If we do take the branch, then we got to go somewhere else. So if you assume that we're not going to take the branch, then you can be pipelining that next instruction. Okay? And then the other reason is because the cache is going to work well that way too, right? Because you'll have temporal locality. What's the problem with predicting that we're not going to take the branch? Yeah? Yeah, right. I mean, if you have a for loop, you're taking that branch every time except for the last time, right? So predicting that you're not going to take a branch isn't necessarily a great prediction. Yeah? Yeah, so that's a really good point or a good idea. So a bunch of systems have fairly elaborate branch predictions, and what they do is they'll keep a cache of what happened last time you hit this branch, and they'll use that as a prediction, and there's a bunch of tricks like that. They typically involve extra hardware, but you can do it, okay? You can also get the compiler to help you, okay? Yeah?
Would you combine this option with the previous option?
So yeah, you'd combine this option and the next thing I'm going to tell you with the previous option to try to get things to go faster. Okay? All right. There's one other thing you can do, which is kind of cool, which is you could say, all right, what I'm going to do is I'm going to change slightly the meaning of a branch. So in the old days, up until 10 seconds ago, the idea was, if you take the branch, then nothing after the branch gets executed. You just follow, you just go to wherever that branch is and you can continue. But you could change the definition of a branch slightly to say, we always execute not only that branch statement, but the instruction right after it, okay? Because remember, we've got that bubble. We've got that one instruction bubble that we couldn't get rid of. We had two bubbles. We got rid of one of them, but we still have one. So what you could do is you could put an instruction after the branch, okay, and that's called the branch delay slot. And if you change your definition of a branch just slightly so that you always execute the branch and the instruction after it, as long as that instruction after it is something that you should have done anyway, this is going to work out pretty well, okay? So this is called branch delay, and this is one of the things that MIPS does. And, here's an example. So, if we've got a bunch of code and we have this branch on equal, what's going to happen is, in the old days, when you go from the branch, you jump to, if you take the branch, then you go to the label exit, right? That's what this is showing. But if you notice, this first instruction, you've got to do that anyway, and it hardly matters if you do it here or here, because it's not touching any of these registers, okay? So what you could do, if you're a clever compiler, is you could put the OR instruction right after that branch, right into that delay slot, okay? And it'll still get executed after you do the branch, okay? And then you end up with the same effect, okay? So over here, we'd have a stall, right? We'd have a stall of we'd have a bubble of one instruction. Here, we fill it in with a useful instruction, okay? So that's kind of a nice trick. So that's called delayed branch, okay? And what happens if you can't find an instruction to put there? What do? Yeah, you put a no-op, okay? And so it's no worse than stalling anyway. Okay, one more question.
Is this then only useful for if it's not looping? Because otherwise, you'd be executing that instruction over and over again.
Well, yeah, you'd want to, if it's something that's supposed to happen inside a loop, I guess, yeah, you'd want to be careful about what you got to be careful about what you put there for sure.
I mean, because every time you get to the branch, though, you'll execute.
Yeah, every time you get to this branch, you execute the next thing. Now, again, that might not hurt anything. After you do it the first time, it would just be a no-op after that. So there's issues about correctness and issues about, if I was a little smarter, could I be more efficient? And you want to make sure you're correct, and then once you're correct, then you can try to be smarter. Yeah?
For the branch prediction, what do we do in the case that we were wrong? Like, how do we have to have another instruction that is the logical opposite of that?
Like an undo. That's really cool. So, So in my field of databases, we do exactly what you're saying. It's called a compensating action. You do the opposite. Like if you added 1 to something, you subtract 1 from it to get back. Here, you don't have to do that. Here, if you've guessed wrong, you'll know. There's this one bubble. After that bubble, you'll know you've guessed wrong. and as long as you keep everybody afterwards from actually updating anything, right? That's why you have to set the control flags to 0. As long as they don't update anything, there's nothing to undo. You just let them finish, but nobody knows what they did because they didn't write registers and they didn't write memory. So it's okay to just let them finish. So you don't have to undo them. But there's definitely systems higher up in the stack that are doing that, exactly that kind of inverse logic to compensate for actions. And if you guys, if I see you again in 186, we'll talk about that kind of stuff. Okay, cool. All right. So branch delay slot, we've probably already talked about this. In the worst case, what do? You add a no-op in that slot. And in the better case, you put something useful. Okay? And so there's this note that the compiler usually finds a good instruction half the time. I'm not sure what that's based on. I assume that there's some justification for that in the book. But you're not always going to get it right. But if you get it right half the time, you're getting basically that many free instructions, which is good. You're getting those for nothing. Yeah.
These two solutions, branch delay and branch prediction.
Yep.
They are mutually exclusive, right? You can't have both of them at the same time.
No, branch prediction, you could do both of these at the same time because remember, the thing that you're putting in that branch delay slot is something that you had to do anyway. So you can still do it.
What I mean is if you have that branch delay slot, you've already filled in all the bubbles before you can branch prediction.
So why would you do this? So it's not could you do it with branch prediction, does it buy you anything? And I think it does. It buys you the use of that bubble slot in the case that you correct, that you guessed correctly. So I think it does buy you something, right? Because if you don't use the bubble slot, then the thing that you put right after, if you don't do delayed branch, then the thing you put right after the branch might be the wrong thing, right? It might be the branch that you shouldn't have taken. And then that's wasted work, whereas this is always work that's useful to be done. So
you're saying that if there's no delayed branch, then it's okay?
if there's no delay, I think let's take this offline because it's a minor point. Anything else? All right, but we can work through it. Okay, so good. So we talked about our 3 main types of hazards. We talked about structural hazards, we talked about data hazards, and we talked about control hazards. Some of them we fixed with clever scheduling, a little help from the compiler. Some of them we fixed with some new hardware, like we put the comparator, the branch comparator, into stage 2, okay, instead of using the ALU for it. Some of it we fixed by trying to do some prediction, okay, which requires either just guessing or some extra hardware. Okay, and all that stuff takes that beautiful single cycle data path that we created, over a couple lectures, and basically made it super, super complicated. But the book does a really nice job of showing sort of step by step, how all these pieces, as you add in sort of each new optimization and each new little bit of complexity, how it fits in. So I recommend that you spend some time, maybe on your 3-day weekend, or certainly before. Before you get to the final and maybe even Project 4, take some time looking at those chapters in the book. They're really nice. Okay? There's one last thing that's covered in this section, which is some more advanced stuff. And this is section 4.10. And what's really funny is if you go and look at this, the first sentence is it says, okay, we're about to spend 13 pages on some additional optimizations. We've written another book that's the upper division computer architecture course. That book has, I forget whether it's 200 or 300 pages on the same topic. Okay, so this is really just a short kind of quick overview to tell you about some other things that are happening out there. But it's just really broad brush. It's really just at a high level so that you get a feel for what some of the design options are. Okay, so. One thing that a few of you guys talked to me about after class was this idea of, we claim that that for a balanced pipeline, The speed up is basically proportional to the number of stages you have, right? So that would argue, why should I have a 5-stage pipeline? Why shouldn't I have 10 stages or 15 stages or more? Okay? And so you could do that, right? Because if you chop things up into smaller and smaller pieces, then remember, our clock can tick at the speed of the slowest stage. So if you make all the stages smaller, you can make that clock run faster. Okay? So, and then you can get more parallelism. All right? So, there is an argument for deeper pipelines or longer pipelines, more than 5. And I'll show you sort of what some modern processors look like. But there are limits, okay? And the limits have to do with our ability to do prediction, our ability to find enough instructions that we can reorder, and our ability to really deal with all those hazards. Okay, so it's not unlimited. At some point, the complexity of the circuitry gets too high because there's too many possible paths through all those different stages. And at some point, there's so many dependencies going on that you're just not able to get any more parallelism out of it. Okay, so that deeper pipelines help for a while. The other thing that's interesting, and this is sort of one of these things where if you felt like you sort of understood how things work, well, here's another level of complexity. And the issue is what's called multiple issue, no pun intended, but multiple issue or what's called superscalar. And the idea is that I can add a little bit of hardware, so it's still within the same core, okay? And it's still within the same, I'm running still one thread of instructions, okay? But I'm going to try to execute I'm going to try to start multiple instructions at the same time. So in pipelining, right, we were sort of saying, okay, this instruction starts and it moves to the next stage. That means we can start the next one. Those move to the next stage. That means we can start the next one, right? So we're sort of staggering one stage at a time, okay? This is saying, let's not even do that. Let's issue multiple instructions at the same time, okay, within the same processor, okay? And so that turns out to be what a lot of systems do today. And it's interesting, if you think about it, if you have a processor where the clock's ticking 4 billion times a second, and you can issue 4 instructions per clock tick, then you can be running at about 16 billion instructions per second. Okay, so your cycles per instruction goes below 1. And in fact, when you talk about these types of systems, you often, instead of talking about cycles per instruction, you talk about instructions per cycle. How many instructions can you get done in one clock tick? And in this case, you can get 4, at peak, in the best case, you can get 4 done per clock tick. Okay? But, it's hard to get that because of all the dependencies and the stalls and the hazards and all that stuff. So let's look at this multiple issue thing. There's 2 versions of it. There's a static version where the compiler figures it out. Okay? And that's the one we're going to spend most of the time on. And the compiler makes sure that it gets it right, it avoids the hazards and so on. And then there's what's called dynamic multiple issue, which is the actual hardware is making the decisions. Okay? And it might change over time based on exactly what instructions are being run at what time. Okay? So we'll talk about these 2. So, the basic idea is if you have more, you can add some resources so that you can basically get more parallelism. Okay? So, what we've done here now is we have, multiple washers, right, multiple dryers, and multiple folders, and so on. Okay? And then we want to pipeline those. All right? So we're going to add resources. That's the trick. Now, just to let you know sort of where things stand, I thought this was really useful. If you go back to, the initial Pentium and even before that to the 486, you sort of see the trends of things. So back in the late 80s and early 90s, Intel chips had 5 pipeline stages. That's kind of a number we're comfortable with. But over time, the number of pipeline stages grew. And what's interesting is you'll see that kind of in the mid of the last decade, they got up to really crazy pipelines, right? 31 stages. Imagine trying to figure out how to make that thing work. Okay? So they ended up getting into trouble with complexity. they ended up figuring out that, okay, maybe there's a better way to use those transistors, right? We've got a limited number of transistors. We can either use them doing this multiple stage pipelines, or we can have simpler pipelines and use the transistors to have maybe more resources. So pipelines went down. Issue with, right, how many instructions do you send out at a time, or do you try to start at a time, just keeps going up. So it used to be just one, then it's going to be two, like we're going to talk about, and then currently it's at around 4. Cores, as we've already talked about, are just going up and so on. So if you look at it, if you just graph those numbers, and again, this is just one company, one set of products, but what you can see is, as we've talked about, clock speeds aren't getting any faster, right? And that stopped around 2005. Power, whatever, it went down a little bit. Now it seems to be creeping up a little bit more according to this. But what's happened is we added more pipeline stages, okay? And then we took the graduate architecture class and we said, oh, that's too many pipeline stages. And we went with simpler processes, right? And then issue with, turns out, seems like we still got some more gas there. We can keep going. And then number cores, again, that's what's happening. As we are getting more transistors, we're using them to stamp out more cores, okay? And remember, the difference between having more cores and having more hardware in a single core is that the single core is going to run one thread, okay? Or a couple of us were talking earlier in class about this thing called hyperthreading, which actually plays some tricks to let you run 2 separate threads, right? A thread is a control. It's a program, basically, or a logical program, okay? The cores are all going to be running separate threads. So in order to take advantage of these multi-cores, you have to do, that's the data parallelism and all the other, and the request parallelism. You have to figure out how to take your program and break it into multiple threads of control. Everything that we're doing on a single core, right, this issue with thing, you write your program the same way. It's just a single thread, and the hardware is trying to make it go faster through parallelism. Okay, so let's look at static multiple issue, and we'll see how far we get on this. The idea is you group instructions into these things called issue packets, okay? And you can submit an issue packet once per cycle, okay? So if you can fit 4 instructions into an issue packet, that means you're issuing up to 4 instructions per cycle, okay? And you could think of this as a very long instruction, right? Because remember, in MIPS, our instructions were 32 bits, okay? Now, what we're going to do in the MIPS is we're going to do double issue. We're going to issue 2 instructions at a time. So effectively, that's a 64-bit instruction, okay? It just says to do 2 things. So what does that look like? Well, it looks like this. In the MIPS architecture with the static dual issue, you get, on a single 64-bit issue packet, you get to put 2 things. One is either an ALU or a branch instruction, and the other is either a load or a store instruction, okay? So these are 64-bit aligned, right, because they're 64 bits. So if you look in memory, what that would look like is, at address N, I've got my ALU or my branch instruction. In the next 32-bit word, I've got a load or a store, and those 2 things are going to run at exactly the same time, okay? And then I'm still going to do pipelining, and the next clock tick, I'm going to issue the next issue packet, and that has, an ALU and branch in the first half and a load or a store in the second half, okay? So that's what I get to do, and the constraints on what I can put in the first half and what I can put in the second half depend on the hardware, okay? So, because remember, I've gone from having a 32-bit instruction to having this 64-bit, mega double instruction, and I've got to take those first 32 bits and send them somewhere, right, and drive all my control. And then I've got to take those second 32 bits, I've got to send those somewhere and drive all the control. So, what I can put in which part of that issue packet is totally driven by the design of the hardware, okay? So, if I've got an ALU and branch and a load and store that are near each other that I can start at the same time, I'll do it. If not, then I'll put a no-op in one of those slots, okay? So I don't always get to issue 2 instructions. So now there are additional hazards that we have to worry about, okay? So we had all the hazards that we had before when we were doing pipelining, because notice, we're still doing pipelining. Now we're just doing it in chunks of 2 instead of chunks of 1, Okay, so we're still doing pipeline. We've got all those hazards. Plus, we've got an additional hazard, which is in the same packet, I've got a load use problem. Okay, so, you know, or actually, this is a use load problem. So I've got, if I'm putting something into T0, and then I'm trying to use that result that's supposed to be in T0, I can't issue those at the same time, right? Because those two instructions are going to be running at the same time. Okay, so I either have to put them in different packets. Well, I do have to put them in different packets. And the question is, do I put no ops or other instructions in there? If I put no ops in the other half of those two packets, then I've basically just implemented a stall. I might be able to put something better than a no op in there, and then I'm getting a benefit. All right, and I'm going to show you an example in a second. There is a load use hazard still, and the load use hazard is still one clock tick. Okay, like it was before. But now remember, every clock tick is two instructions, not one, right? So now we've got a you know, logically a bigger bubble, even though in time it's the same amount of time. It's the time for two instructions instead of the time of one instruction. So we have to handle that case. Okay, so let's do an example, and I think this will make it clearer. So here's our program, right? We're going to load. We're going to do an add. We're going to do a store, add, and then a branch. Okay, so we've got those 5 instructions, and we've got we've got an issue packet of size 2, right? Because we're doing dual issue scheduling. Okay, so now let's try to schedule these things. So let's schedule the first one. So we want to do this load. Okay, well, loads have to go in this half of the instruction, right? In this half of the issue packet. Okay, and we don't have an ALU instruction we can do. Why? Because this add needs the result of the load. Okay, so we can't put those in the same issue packet. So we're going to put a no op in that first half. Okay, that's okay. Now in this case, we also have a right. We have a load use problem here, so we can't even put it in the next packet, right? Because we've got a delay, right? We've got a bubble of one clock tick. Okay, so we've got to find something else to put in. Well, we can't put that store because we don't know what the new value of T0 is. So the next thing we can put in is this add I. Okay, so the add I goes in on the ALU side, and we don't have a load or a store that we can put in, so that goes over here. Let me get through the example. All right, so we'll do a no op there. Okay. Now at this point, we're past the data hazard for this load use hazard. So now we can do the add, and we'll do that in the ALU branch. And then so far we've earned absolutely nothing by doing this, right? But hopefully, oh, there we go. Good. Okay. So now we can do the branch at the same time that we do the store of the answer we've computed in T0 back into memory. Okay? So, you know, we got a little bit of a boost here. Not a huge boost, but we basically got a quarter boost. Okay? Because we got to run, you know, this was one instruction. Then we got to run basically this instruction for free. Okay? And the more you look at, the more code you're able to look at, the more likely it is that you're going to be able to fill in these no-ops and get the advantage of that extra parallelism. Okay? Yeah?
Why would you pick ALU branch and then load store over load store? Or could you optimize to do whichever one is better? Because if you switch them, then I think you could like make the first one without a no-op, for example.
Yeah, we only got a few minutes left, so I don't want to, it might be possible to optimize this one. You just have to make sure you respect the delays in the data hazards. And if you do that, sure, so we can look at it to see if there's a better way to do this, right? But this actually gets to the point, which is, you know, this is all about having a smart compiler, okay? And the smarter your compiler is and the more code your compiler can look at, the better chance you have of actually filling in these slots. But the important thing here is there's two important things here. One is this concept of getting additional parallelism in a single core by issuing multiple instructions at the same time. Okay, that's the key point. And the second point is that there are constraints, right? All the hazards that we had before, plus an additional hazard that has to do with, that you can't, there are hazards now within an issue packet, right, that you have to worry about. So you have to convince yourself that this is correct, right, that it gives you the right answer, that it works. Then you can also think about optimizing it. Can you do a better job of making it more efficient? Okay, now you guys, I can tell, you guys spend a lot of time thinking about loop unrolling, so I'm not going to tell you anything about it that you don't already know. But the key thing about loop unrolling is if you do it, you get more instructions to look at, right? And again, that was our problem here. The reason why we only got to have one dual issue is because, we only had these 5 instructions and we had a lot of dependencies between them. If you unroll your loops, then you've got more instructions to look at. You can get more parallelism, okay? So that's all I want to say about loop unrolling, okay? And again, you've got the slides. Dynamic multiple issue, again, what we're going to do there is that the hardware is going to be making the decision, not the compiler. In order to do that, you've got to be able to, the hardware has to be able to reorder instructions. So it has to understand dependencies. What instruction is waiting for the answer of what other instruction. It can run those things at the same time, but it can only let an answer out at the right time. And so what happens with dynamic scheduling is the hardware is doing reordering. It's got extra buffers or extra registers to keep results, and then you need control signals to let those results go out at the same time. It's much more complicated. If you look in the book, they'll tell you more about it, okay? Finally, and one more technique is this idea of speculation, that you can do better by understanding your program, figuring out which way branch decisions and other types of decisions are going to go, and then setting up, you do your reordering that way. Okay, so there's a little discussion about that in the book. Okay, bottom line is, if you had a hazard like this, where this was the example where your socks got split up into load A and load D. Well, in that case, you'd have to wait. You'd have this delay. You'd have to wait until everybody would have to stall, basically, until you got your second sock. If you have enough extra hardware, you can actually reorder things and just keep going. So this is another example that's in the book. All right. Just quickly, this stuff isn't science fiction. Processors today do multiple issue. We talked about dual issue. The current Intel chips are doing 4, and they're all doing some sort of out-of-order operations and speculation. So that's just standard practice now in the industry. All right. Does it work? Yes, it does. That's why people do it. But there's a limit because of all the dependencies and the hazards and the things we've been talking about, okay? As well as other types of delays like memory delays. All right. So 3 o'clock, let me just wrap up quickly. We've taken a long walk through the design of a CPU. We started off really simply, building up from the transistor level up. We built an entire data path that ran in a single clock tick. We split it into pieces to get parallelism, and then we looked at even more ways of getting parallelism by adding some resources and then running multiple instructions, starting them at the same time. So hopefully it was a very logical progression. If you look in the book, they take you through that exact same set of steps and are very careful about drawing which wires come from which register and go to which control signal. And so, take some time and make sure you read through that and understand how things fit together. But hopefully, you now have a real good feel for, how we bridge that gap from the high-level programming language, all the way through the machine code, and then how that actually translates into circuits that actually execute your programs. It's been a long trip, but we've done it. So with that, take a long weekend on me, and when we come back next week, we're going to hear about virtual memory and some other things about how to put the whole system together.